Good morning, my audacious audience. Welcome to our show, What, Why, and How. I'm your host, David Zhang, and today we're going to be answering the question, what is light? Ever since the beginning of humanity, we've been interested in the night sky. I mean, just look at it. It truly is beautiful, and mysterious too. It makes sense why we've been staring at it for thousands upon thousands of years. In 2014, Christopher Nolan directed Interstellar, one of the most astronomically inspiring movies out there. That movie, along with the rising number of other popular films related to astronomy, such as the new Star Wars or Star Trek or MCU's Avengers, Guardians of the Galaxy, etc., are what inspired the series. Over the course of 10 episodes, we'll be exploring the many elements of our universe, including the nature of black holes and Einstein's theory of general relativity. But first, let's start with the basics. What is light? So let's go with something familiar. Light bulbs, fire, lightning, glow sticks. All these light up the dark and help us see. All these things give off what we call visible light. This diagram represents what we call the electromagnetic spectrum. The full length of the spectrum represents all light, but only this small section, 0.0035%, is visible to human eyes. To better understand this diagram, we first have to understand light's wave-particle duality. While this may sound complex, it really just means that light behaves as both a particle and a wave. That may sound paradoxical, but don't worry. According to quantum mechanics, all particles have a wave nature and vice versa. Now, it's easy to say, oh, well, this theory says it's not counterintuitive, even though it still is, so there, just accept it. But without diving deep into quantum mechanics, just think of it like this. Light particles are called photons. Photons are theorized to be massless and travel at the speed of light, about 300 million meters per second. That is denoted as c in Einstein's equation, E equals mc squared. If it helps, you can imagine photons oscillating in the shape of a wave, but this isn't quite correct. What really is happening is that the probability that a photon is in a given spot can be described using a wave function. And not to confuse you, but there are ways of describing photons as having mass, but the current model of a massless particle is more helpful in understanding the basics of light. So, now that you have a grasp on how light behaves, let's go back to the diagram. The electromagnetic spectrum is a wave spectrum stretching from super long wavelengths, lengths of football fields, to super short wavelengths, smaller than an electron. If you aren't familiar with the properties of waves, the wavelength is the distance between two consecutive peaks, or two consecutive troughs. Another property is frequency, or how many wavelengths pass per unit time. Usually we use 1 second as the unit of time, giving us a frequency in hertz. As you can see, wavelength and frequency have an inverse relationship. As one increases, the other one decreases. Back to the spectrum. Different ranges of wavelengths of light are given different classification names. The longest wavelength is called radio waves, and what we use for wireless communication. Next are microwaves. Yes, your microwave at home basically blasts your food with a bunch of radiation at the wavelength of microwaves. Don't worry, the radiation is safe to eat. Don't put yourself in the microwave. It excites water molecules to heat your food, and you're mostly water, so, don't put yourself in the microwave, in case you ever thought of doing that. Then infrared, which is what heat radiates, followed by visible light, all the colors of the rainbow, from red to blue. Then ultraviolet, which is high enough frequency to cause some serious damage to humans, like skin cancer. Or it could purify, water. Next comes X-rays, which is convenient because it goes through less dense objects like your skin and organs, but not as well through more dense objects like your bones. And inconvenient, because prolonged exposure in the wrong places will give you cancer, and you will most probably die. And finally, gamma rays. No, you will not turn into the Hulk. You will die. Please do not aim at things you do not wish to kill. As dangerous as the high-frequency light waves are, they do have many beneficial uses, such as killing cancerous cells. They are mainly used in the medical field, so unless you have a medical need, please stay away from gamma rays. As you can see, we use light to do so many things here on Earth. Astronomers use telescopes to observe light from the rest of the universe, and they can calculate and deduce so much information using this data. It's unbelievable. Next episode, we'll discuss the universe's greatest sources of light.